Okay, those who study calculus. For the homework assignment, there's this first question right here. And then I'll be honest, I'm feeling a bit lazy. I'm just going to keep the video that I made for my last year's students because I didn't change anything for the multiple choice part. And then there's there's only two multiple choice questions, 1 and 2. And then 3 and 4 are free response questions. But I didn't have this one for them last time. We did something like this in class. And so, yeah, I'm just going to do a video on this first part right here. And then I'll post the video that I made last year for these questions. Yeah, hopefully that should be enough. I honestly don't remember what it's like, so hopefully it's good. Okay, but for this first part, we're talking about optimization in 510 and 511. And optimization is basically just finding absolute minimums and maximums with real world with some context rather than just in functions. So here we have Charlie, and Charlie is constructing an open box from a rectangular piece of cardboard. Kind of like, you've probably done this before, maybe like elementary or junior high or something. You get a piece of paper, you cut out some corners right here, and then you can fold up the corners, and then you can make a kind of rectangular box right here. So it's given us dimensions. So we have 40 centimeters and 46 centimeters here. He will cut equal size squares, so these will be the same length. So all of these squares right here are gonna be equal length. So x and x, 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 x. Okay. What should x be to maximize the volume? So how much should I cut in order to get the most volume possible in this cardboard? So this is an example of optimization. It's just you're trying to maximize something. So it's always important to know what you want to maximize. Kind of keep this in mind, because basically what we're going to try and do is just make a function of volume. So if you can start there, it's actually really cool, because then you can just start building out what you know. So what do I know about volume of a cardboard box? A volume of a box is length times by width times by height. Now, this isn't really a function because we have length, width, and height. So is there a way where I can take length, width, and height and define it in terms of x? Because that's really what we want to do. We're trying to maximize volume, but we're trying to see what value of this x right here is. Now, if you think about this cardboard box, this is what we're folding up, right? So whenever we make this cardboard box right here, we'll have this base right here. This is the base, okay? You're gonna see how well I can make this cardboard box, all right? My drawing skills are gonna be on display right here. So you have a cardboard box. I'm gonna cheat a little bit because I can. So, okay, maybe do something like that. Okay, follow me here. Okay, keep following me here. So we got, boom, got the base right here. And then since we're gonna have these corners right here that's going to be cut up, those are the corners that are going to fold and they're going to meet. So we're going to meet something like this right here, and that's going to be the height. So this is what our cardboard box should end up looking something like this right here. So that means that the height right here is actually just whatever we cut out. So the height is equal to x. Okay, now what about the base right here? What is the length of this side right here? So the length of that side, we know that the length of all of this right here is 46. And since, let's think about it like this right here, all of that right there. If this is x and this is x right here, let's call this one the length times width. Let's call this one the length or something. We'll call that the length. We'll call this part right here the width. Okay, so what is the length equal to? Well, if I think about it, the length is going to be equal to 46 minus 2x, because we're taking the entire length right here and subtracting away 2 of those x's right there. And then for the width, that's going to be similar. We're just going to take the total length here, which is 40, and subtract away those 2 x's, so 40 minus 2x. So now that we know that right there, let's define volume. So volume is a function of x, and x is the same thing as the height, but we're going to take the length, which is 46 minus 2x, times by the width, which is 40 minus 2x, times by the height, which is x right here. So now we have a function of volume. I'm going to, unfortunately, FOIL this out because I want to do this by hand if I can, which I probably won't be able to because these numbers are going to be stupid high. So FOIL this out, so 46 times by 40, and I say I'm going to do this without a calculator, but then I grab a calculator so I can do this stuff right here. That's going to be equal to 46 times by 40 is 840. And then 46 times by negative 2, that's going to be equal to 92, so minus 92x, then minus 80x, then plus 4x squared, and then times by x. And then if we clean this up, we're going to have 140x, and then we're going to combine these, so negative 92 minus 80. So it's negative 172, so negative 172, but we're going to multiply by the x out here, so it's going to give me x squared. I don't know if I said that before, but we're distributing the x too. So the x, and then that's going to be plus 4x cubed, so plus 4x cubed. So I'm going to show you kind of what the graph looks like, but I'm going to show you how do we use calculus right here? How do we use calculus to help us maximize? And we're going to use calculus the way we've been using calculus in chapter 5 in finding minimums and maximums. But let me go ahead and graph what this function looks like. So we have 1840, so 1840x. Then we have negative 172, so minus 172x squared. And then we have plus 4x cubed, plus 4x to the third. Now we're going to have to really size down this graph right here because the numbers are very, very large. Let me size it down. All right, it's going to make me do this. Okay. There we go. Okay, so here's this graph right here. Now, this graph is a graph of volume. So it's telling me what the volume of the box will be. So the y-axis, these dimensions right here is the units of volume. The x-axis is the units of the height. So for example, when the height is 2 centimeters, the volume will be something close to 3,000 something, 28, 3,030 or something, 3,028 centimeters cubed. So this is what this is right here. So obviously you can look at this graph right here and see when does it reach its maximum. So it's going to reach its maximum right here at whenever the height is 7.1145 centimeters, and the maximum volume it's going to have is 5,825. Now you might be asking, well, wait a minute, what about over here? Now, since we are using context, to the left of the origin, it doesn't really make sense to use anything to the left of the origin because that means centimeters are negative, which it can't be. Now, what is the maximum that this right here could be? Now, if you think about what's the largest square I can cut out? Well, if you cut out a square, so let's say we take this shorter length right here and make this 20. So 20 centimeters. So if I take a 20 centimeter box right here, so 20 centimeter, so 20 centimeter, this is going to be a very, not a great box because you're basically just going to have to fold right down the middle. And then in that case, you're not going to have any volume because you're not going to have a box to begin with. And so the domain of our volume function should be between 0 and 20 centimeters. Okay, now you can see that here because if you look on the graph right here, 20 is, if you go anything greater than 20, you're going to have negative volume. which wouldn't make sense either. So our restrictions are between 0 and 20. That's the largest value we can cut into. We can make x in order and still have a box. We have to be somewhere between 0 and 20. Okay, now how do I show this with calculus? Now remember what we've been talking about. We've been talking about calculus. How do I find minimums and maximums? When does a maximum occur? A maximum occurs when a function goes from increasing to decreasing, and that's going to change when the derivative is 0. So right here, whenever we have this function, so this is we'll call it v of x, sure, we'll call this v of x right here, equals that. What we're going to do is we're just going to simply, well, let me just show you with a graph. We'll do v prime of x. So v prime, even though we're going to do this by hand, so v prime of, v prime of x. Yeah, that's what I want. So v prime of x, if you look right here, so v prime of x is going to where it's equal to 0 is the same value where the function obtains its maximum. So it's just what we've been doing all this whole unit in terms of finding maximums and minimums. So how do I find the maximum volume? We're going to use calculus. So we're going to find the derivative. So v prime of x is going to be equal to 1840 minus 172 times by 2 is going to be 344x plus 12x squared. Yep, just like that. Okay, and then what we're going to do is we're going to set this equal to 0, and we're going to solve for whenever the volume is 0, when the derivative is 0, and that's where we're going to find its maximum. Now, you are going to have to use the quadratic formula. So x is going to be equal to 344 plus or minus the square root of 344 squared minus 4 times by a times by c all over 2 times by a. Now remember that this produces two solutions right here. This is going to produce a positive and negative, so you have to keep that in mind. This one does have two solutions, but this other solution is going to be outside of our domain of which we said it could fall in between. But in any case, you can use the quadratic formula, and whenever we solve it, we're going to find that when x is equal to 7.1145 right there, that's when the that's the amount, that's the largest that you want to cut these squares in order to produce the largest volume for this box right here. So it's pretty cool. That's optimization right there, and it's pretty fun. Okay. Anyways, I think that's it for that one, and then you should be able to see the other video for the rest of this right here. Okay.